So now let's begin with linear equations of second order with variable coefficients. In the earlier classes, like when we explained about the module 1 and the module 2, we have seen linear equations of second order with constant coefficients. Because the coefficient is same when we found the method of variation of parameters or the RHS values and all, we have the constant coefficient. But here we are having the variable coefficient, means coefficient is not constant, it varies. So in that case, we would have two type of variable coefficients, means we have the linear equations with variable coefficients is divided into two types. One is homogeneous equation and the other is non-homogeneous equation. The homogeneous equation, we are having two types, two methods to solve homogeneous equation. So first method is Euler type or Cauchys Euler type. This method we are going to see as the primary section, and the second method is Legendre's type. So this is the second method to solve homogeneous equation. And the second type of linear equations with variable coefficient is non-homogeneous equations, and we don't have any method to solve this. We don't have no general method to solve non-homogeneous equation. So as we don't have any methods here, we will be concentrating on homogeneous equations and how to solve, and we will try the Euler type first and the Legendre's type second. So let's begin with the Euler type or Cauchy Euler type. So now let's see the homogeneous equations of the Euler's type. So recently we have studied there are two types of homogeneous equations, that is Euler's type and the Legendre's type. In this video we are going to see the equations based on the Euler's type. So let us see what is the difference or what is the change occurring in the Euler's type. It is nothing but we will have the equation in this format. This is how you understand a question is in Euler's type or in Legendre's type. So the Euler's type question means Euler's Cauchy's type questions will be in this format. This is the equation format of Euler's type with variable coefficients of the homogeneous equation. So that is x to the power n into d to the power n into y by dx to the power of n plus a1 into. So here we are getting a constant, a1 is a constant. So from the second term a constant a1 is multiplied along with x value will be decreased by 1. If it is x square, it will be x to the power 2 minus 1 means it will be x. If it is x square, this value become x. If this is x cube, this will become x square and next value become x. So in that way x value will go on decreasing by 1 power 1. And one more change occurring is here d to the power n. Here also n value will be decreased by 1 degree. Here also x to the power of n will be decreased by 1. And in the next time you can find again a coefficient will be multiplied along with, also the power will be again decreased by 1. Here it is n to n minus 1, here will become n minus 2. Next it will become n minus 3, n minus 4 and so on. Finally, we will reach a stage where we will get the coefficient to the or the constant to the maximum. The constant will be maximum, that is a to the power of n. This is the nth number maximum into, at that time what happens, the x to the power will become x power n minus n means x power 0, that is equal to 1, and this time also becomes 0 because the power becomes d to the power of n minus n means d to the power of 0. Again we don't want to write that time, so this whole time will get deleted into y. That is the last time you will get. Okay, so this is the last time you will get. Fine, that is equal to f of x. This is the format of Euler type equation with variable coefficients. Okay, fine. Now we got a question of the Euler's type. Up to that it is completed. Now what to do next? That is a big question. We don't solve a question in variable type directly. If we have a question in variable coefficient, we don't solve it directly. There is a conversion process in the middle. This is the next step. That is known as conversion. We have to convert the linear equation with variable coefficient to constant coefficient. Means we are converting the term with variable coefficient to the constant coefficient 1. This is another important change you have to notice. We have to convert. So how we will convert? By substitution. We have to substitute certain values for this conversion process. That is, there are two main substitutions. One is we will replace the x value by e to the power of z, or z value by log x. This is one of the substitution, because if x is equal to e power z, if we take log of z, we will get it is log x. Z is equal to log x. That we know it automatically. Just it is the continuation of this. And one more change is, if the question is in the format x into d into y, we can write it as d dash into y. That is another important change. We have to write x into d, replacing x into d by d dash. And if it is x square into d square, if the question is in the format x square into d square, we have to substitute by d dash into d dash minus 1. Similarly, if it is x cube into d cube, then we have to replace by d dash into d dash minus 2. So now please, if it is x to the power 4 into d to the power 4, it will become d dash into d dash minus 1 into d dash minus 2 into d dash minus 3. So this way it goes. These are the basic theory part of how to solve a homogeneous equation in the Euler's type. There is a conversion process in the middle by substitution that you have to note. So now let us enter into a problem of the Euler's type. So here we have the question: solve x square d square minus 7x into d plus 12 into y equal to x square. But when seeing the question, you can understand this Euler's type by seeing the powers mainly. It is in the format of x of d into plus a1 into f x of d into a to the power of n into y, right? So we can understand here. Here we are having power 2 reduced to power 1 reduced to power 0. So clearly this is a question from Euler's type. So let me solve this equation. So in the Euler's type of homogeneous equations, we have studied that we have to make some conversion, changing from variable coefficients to constant coefficients by substitutions. So what are the main substitutions? One is put x is equal to e to the power of z. This is one of the important substitution we have to make. Another substitution is put z is equal to log x. That is another substitution you have to make. We can also write this as log x is equal to z. We have to replace log x by z. Another important substitution. And the next thing is substituting x into d is equal to d dash. Similarly, x square d square is equal to d dash into d dash minus 1. We have to write only up to x square d square because the maximum degree is x square here. So this is the maximum replacement. So these are the things you have to replace. Now let's go on solving the problem. So after replacing, we get this as x square d square, means we have to replace by d dash into d dash minus 1. So d dash into d dash minus 1 minus 7 into xd. xd means d dash plus 12 into y equal to x square. So x we have to replace by e to the power of z. So replacing e power z whole square. So now we have replaced. Now we have to go on solving. By going on solving, I can write this as d dash into d dash square minus d dash into minus 1 minus d dash minus 7d dash plus 12 into y equal to e to the power 2 into z. When powers are multiplied, we can write 2z. Okay, that implies d dash square minus d dash minus 7d dash means minus 8d dash plus 12 into y equal to e to the power of 2z. So we got this in this format. Now we can find the complementary function for this. So here also similarly, first we have to find the complementary function, then the particular integral. Now let's go on finding the complementary function here. So the complementary function, to find the complementary function we have to write the auxiliary equation. So auxiliary equation is, so d dash square means we can write it as m square minus 8d dash means 8m plus 12 equal to 0. That implies m square minus 8m plus 12, is it? So the last number is even number, so we can take factors for this. That is m square, so minus 4, and we can split the 2, right? So I can write it as minus 6 minus 2, minus 6m minus 2m, because minus 6m minus 2m gives minus 8m when added. Addition gives minus 8m, and when these are multiplied, minus 6m into minus 2m gives 12m square, means the multiplication of first and the last time. So these are the correct factors. Plus 12 equal to 0. That implies, taking m as common, m minus 6 in the first two times, I can write as m into m minus 6. Taking minus 2 as common in these terms, I can write it as minus 2 into m minus 6. That is equal to 0. So that implies m minus 6 into m minus 2 equal to 0. That implies m is equal to 6 or m is equal to 2. So here you can find we are having the roots which are real and different, because m is equal to 6, m1 is equal to 6 and m2 is equal to 2. These are real numbers but are different. So when roots are real and different, we have the formula to find the complementary function. Complementary function is equal to a e to the power m1x. So here we have to write a e to the power 6 a e to the power m1x. So just writing the formula, as it is a e to the power m1z plus b e to the power m2z. So this is the formula. So by substituting the values of m1 and m2, we can write it as a e to the power of 2z plus b e to the power of 6z. So this is it. And now you can write this as, by writing the powers in the format, you can write it as a e to the power of z whole power 2 plus b e to the power of z whole power 6. So I am writing this in this format to apply the formula, because we can replace e to the power of z by x, because we know x is equal to e to the power of z. So replacing the value, what we get, that is a e to the power of z replacing by x, ax square plus b e to the power of z replacing by x, bx power 6. So this is the complementary function by using the Euler's type. Fine. Now let's go on finding the particular integral. The particular integral for this. So we know the formula to find the particular integral is 1 by f of d into capital X. So that is nothing but 1 by f of d is equal to this term, the left hand side term, 1 by f of x term. So 1 by x square, or I can also write this as 1 by x square d square minus 7x into d plus 12 into x square. That is the RHS term. Also, we have to replace the terms here, is it? So by replacing the terms, we can write this as 1 by x square d square means d dash into d dash minus 1 minus 7 into xd means d dash plus 12 into x square means e to the power of z whole square. Because we know x is equal to e to the power of z and x square d square is equal to d dash into d dash minus 1 and xd is equal to d dash, as we mentioned in the beginning of the problem. Just replace the values. Now, by going on solving, 1 by d dash into d dash minus 1. So what we get the value? It is d dash square minus d dash minus 7d dash plus 12 into e to the power of 2z. That is equal to 1 by d dash square minus 8d dash plus 12 into e to the power of 2z. Fine. Now we got this in this format. So the next step is to substitute the value. So it is in the format of e to the power of ax or e to the power of az. So then when the RHS value it comes in this format, e to the power, we have to replace the a value in the d square and the d respectively. So we know replace d by a, that is the formula. Replace d by a, and here a is equal to 2. So replacing d by 2, that is equal to 1 by d dash square means 1 by 2 square minus 8 into d dash means 8 into 2 plus 12 into e to the power of 2z. That is equal to, going on solving, 1 by 2 square 4 minus 8 into 2 16 plus 12 into e to the power of 2z. That is equal to 1 by 12 plus 4 16, 16 minus 16 0, 1 by 0 into e to the power of 2z. Here what happens? ODE fails. We can, because 1 by 0, we got 1 by 0 which is infinite, so ODE fails here. So what to do? When ODE fails, we know we have to take the f dash term of the question. So by taking the f dash term, that is the formula, you know the formula is z into 1 by f dash of d into capital X. This is the formula. By applying this, we will get z into 1 by f dash of d. So taking f dash of 1 by differentiation of f. So what is the f of d? F of d is, we know, x square d square minus 8d dash plus 12. So d dash square minus 8d dash plus 12 into capital X, hence the right hand side value, e to the power of 2z. That is equal to z into 1 by differentiation. We are differentiating this term. What we will get? D dash power square becomes 2d dash, 1 by 2d dash minus 8d dash becomes 8, 12 becomes 0 as this is a constant number. So into e to the power of 2z. Okay. So we have substituted, now it's time to replace. So we have to replace d by 2. So replacing d by 2, we get z into 1 by 2d dash means 2 into 2 minus 8 into e to the power of 2z. It's just nothing but I am replacing d by a. replace d by a, and a is equal to 2 here. Fine. Let's go on solving. Z into 1 by 2 into 2, 4. 4 minus 8. So 1 by 4 minus 8 into e to the power of 2z. That is equal to z into 1 by 4 minus 8 means 1 by minus 4 into e to the power of 2z. That is equal to, as 1 by minus 4 is a constant time, I am taking it out first, minus 1 by 4 into z into e to the power of 2z. So this is the particular integral. I can also write this term as minus z into e to the power of 2z by 4. So this is the particular integral. Now it's time to replace these values by substitution, because we know minus z is equal to log x. So we have written in the beginning of the problem, we have to replace z by log x. So replacing z by log x into e to the power of z whole square. I can also write this as e to the power of z whole square, is it? And we know e to the power of z is equal to x. So log x into x square by 4. That is equal to minus x square by 4 into log x. Fine. So this is the final form of the particular integral after substituting the values. So this is it. Now we have got the particular integral 2. Now let us write the final solution. So final solution y is equal to complementary function plus the particular integral. That is equal to, so what is complementary function? We have found it in the beginning of the problem, that is a to the power of a into x square plus b into x to the power of 6 plus the particular integral value, that is minus of x square by 4 into log x. So this is the complete solution of this problem using the Cauchys Euler type. So hope everyone understood the problem. So this is like the initial problems only the change we made is, the change is only in substituting the values that we have replaced the values in the beginning. Other than that, there are no much changes when comparing to other methods like method of variation of parameters and all. Only the substitution process is only a different thing in the Cauchys Euler type, or I can tell it as in homogeneous equations of variable coefficients. So thank you for watching the video. Hope everyone understood this class, and the next class we will be dealing the Legendre's equation, how to solve the homogeneous equation of the Legendre's type. So thank you.